Okay, so I am recording it now.
Okay. So yeah, I wanted to, basically, I'm not sure exactly how much reading everybody has done. There's so much to do, and it's already so dense to actually just start reading through this. But Ella and I have been reading through all of section 4 of all of section 4 of the IMT paper, which is the part that you asked us to verify, and then, or sorry, section 3 of the IMT paper, which is referencing section 4 of the Hughes paper. And so in doing that, we've made it to the first two and a half lemmas, and we found a series of typos and arguments that could be refined a little. And that we were hoping to just check with you to see if you agreed. If you agreed in each case, I think a lot of the typos are just super straightforward, just like, oh, they typed this wrong. And then, and also I was hoping that you could explain a lot of some of the files that you sent. I don't know if it was yesterday or the day before yesterday, but for example, there's one where there seems to be a big project from 2018 from somebody who tried to extend the support to 1/n-3, and maybe I thought before we try to understand the whole thing, you could try to explain where this went wrong, if you remember, or what actually what they needed in order to complete the argument. Yeah.
I'm just sending you everything I have. If things go well with 1/n-2, then we can go up to 1/n-3 and look at that. But I would prefer not to try to extend the support even further until we can get 1/n-2 to work.
Mm-hmm. So we should just not think about that secondary.
I would not think about that for now. I just want to just send you all the notes I could quickly find. I know some people are considering taking a gap semester. And so if somebody is, there's plenty of stuff here for a really good project. And there's a tremendous nucleus. There's a really good game plan going forward. What is needed is time, care, and patience. The place where the greatest creativity is going to be needed is trying to come up with a reasonable analog of hypothesis S so that number theory and random matrix theory agree. You can always just use exactly what you need to make everything agree, but that's not exciting. So the question becomes, which lemmas are wrong, which lemmas are right, which lemmas need to be changed.
Well, should we maybe start going through any potential mistakes or things that could be refined?
Sure. Do you want to punch something up?
Yeah, I can screen share.
Okay, give me just 1 minute.
Yeah.
Okay, are you punching it up on the screen?
Does that now? Okay. Yeah, you should be able to see the two PDFs.
Yes.
Yeah. Okay. So here's some working list of some pretty. Some of the typos are a lot more straightforward. So, for example, page 11, they say notably they're the same statement resulting from lemma 4.5 of Hughes-Miller, but they actually just mean 4.2. 4.5 is something completely different.
Okay.
Yeah, so that could be rectified. And then, so page 42, there's a couple of typos as well. They say under B.11, yeah, they say that the contribution to A from terms where, from terms or whatever, and they actually just mean the contribution to B since they're talking about
Yep.
this thing over here. So that throws off for a while because we were like, oh, where is this A? Just looking through the whole
Right.
document. Yeah. And then they also say right below that since n is prime, if the GCD isn't 1, then the GCD is Jn for j equals 1, 2, etc. And
Right.
so this was super confusing because then they start using in the sum. But what they actually mean is that then B is equal to
Yes.
N. Yeah,
Yes. Yes, you're correct.
yeah. So this definitely needs to be rectified. And then from here it makes sense.
Although, right.
And then from here they also this entire thing should be inside of the exponent as well.
Yep. So that's a clear tech error in terms of the curly braces.
Yeah. And then so something that's a little more, I'm not sure that if this is really something that fully needs to be rectified. It's up to you to say like how refined these arguments need to be. But basically so here when they actually give the wrong approximation here, so they say, okay, this Kloosterman sum has to be bounded above by j to the 1/2 plus epsilon n to the 1/2 plus epsilon. But if they were actually, so I actually did this whole bounding thing, and if they want to keep the same epsilon from above, which they've been using, into the epsilon, like if they want to keep everything right, it should be j to the 1/2 plus epsilon over 2 and n to the 1/2 plus 2 epsilon. And then you can do this whole thing again, and you basically get the same statement, only you don't have to use the epsilon prime, and you just end up with I have it somewhere. Yeah, you just end up with this at the end, n to the minus 5 halves plus 3 epsilon plus sigma n to the n minus 1, which is absolutely enough in order to get it to be vanishingly small. So you can basically end up with the same argument, but it needs to refine some of these exponents in order to keep using the same epsilon and skip using epsilon prime.
So it's good that you caught this. What you have noticed is a mix of two different notations. And a lot of times people state that epsilon is only the same epsilon from line to line, which becomes terribly confusing.
Mm-hmm.
And so sometimes you then change earlier epsilons to make everything work out at the end. I think it's much better to just keep things explicit and put in, now we need this to be epsilon double prime or triple prime or 1/3 epsilon or something like that.
Yeah, it's rough because they use in the previous lemma they also use a lot of like epsilon and epsilon prime, but to use like very specific values that they took to make a certain bound work out, and then they use epsilon double prime as just like a generic small thing, and so it's kind of confusing to go through. So yeah, if I just rewrote this part to be a little more explicit and just use the same epsilon all the way through until you talk about the error term, and so
Yep.
yeah, so that would be.
If you have the tech file, you can just make these changes after you're talking to me directly onto them.
Okay. Yeah, so then all this stuff. Yeah, so that's the typos so far in IMT. Wait, Ella, did you have anything you wanted to bring up as well here?
Yeah, I think you covered most of them. I do have a thing with the equation B6, if you can scroll to it.
Mm-hmm.
There's like a very tiny tech error here for like having the prime and the superscript.
Oh yeah, yes.
Yeah.
It's like the slash sidestep command, which is often used incorrectly, is that the prime should be to the right of the summation, not the upper bound.
Yeah.
Yes.
But I think, well, it's also mostly redundant because the prime means that they're summing over distinct primes, whereas here they have both, which is what.
Yes.
Yeah. Wait, was that the problem, Ella?
Basically.
I mean, we do have the subscript that it's distinct.
Mm-hmm.
So in some sense, we actually don't need the primes.
Also, kind of leading off that, I know Fernando, you'll notice that as well. You probably looked deeper into that. So for equation B2, if you can scroll down to this one.
Sure.
So the W thing. Okay, so here, they're referring to applying lemma A1 of HM with x equals y equal n epsilon. The complementary sums are of size, yada, yada, yada. So basically they're referring here lemma A1 of HM, but they're not really defining it, while HM actually refers to not only x and y's, but also w's. Here they absolutely do not consider the w's, but are still using w's as if it was w equal to n.
Yeah, this one, they actually use w equal 1, sorry, just to.
Oh yeah, sorry, yeah.
And I know this is one of the advantages of taking n to be prime, is it gives us a lot more freedom in what x and y are. In terms of if we want one of them to be large, for instance.
Yeah. In general, parts of lemma 8.1 I was going through, this is one of the things that I think could be really cleaned up, because this is one of the cases where they do that whole thing where they just use epsilon and epsilon prime to mean very specific values that make a certain inequality work out. And then epsilon double prime is just a generic error, and it can be pretty confusing. So I know this has already been published, but it could be something that could be made a lot clearer if you would be okay with like cleaning up some of the notation.
Yeah, and again, I can give you the tech file for Hughes Miller so that if there are things that you want to change, we can change them. As much as possible, it is good to refer to something that's already been published. But if you do want to do changes, we can definitely do that.
Yeah, I mean, there's a lot of notational stuff I noticed in Hughes Miller as well, where they forget just pretty basic stuff, really. Like they forget some absolute value signs. One of the lemmas is typed up really wrong, so it's kind of like it's two statements and it's unclear what the first statement is and what the second statement is, and you need to go through like ILS to figure out what lemma they're actually referencing. There's one thing here. Yeah, so I wasn't sure if this is just the way that you use the notation with the double less than signs, but why do we use like double less than signs here when it could just be an equal sign? Like, is that a typo, or is that because we want to like, is that just how it works when you're making a chain of these?
It's also just safer to do it that way. So when you don't care about what the constant is, if you do a double less than sign, if something changes in one spot, for instance, if one of your arguments is slightly wrong and you have to put in a constant of 50, if you had a strictly less than, you might worry, is it still true?
Mm-hmm.
By putting a double less than, you give yourself a little bit of protection.
I mean, here, an example like this, all I mean is like they have n to the minus 1, n to the 1, and then they just cancel out this minus 1 and 1.
I mean, there, if you want to, you could use an equal sign. It is exactly equal. I agree.
Okay. No, I know this guy doesn't matter. I'm just not super familiar with the notation.
But what if on the left side of the double less than, what if you had not n to the minus 1? What if you had 50 n to the minus 1? Because we have a double less than there, so we could have an arbitrary large constant there.
Yeah.
And so it's just, just to be safe in tracing things. You are correct that it doesn't really matter. And because we have a double less than, any constant can be absorbed in that double less than. But I'm just worried, what if there was a mistake made and in that middle expression, it should have been 40 times that. And now if somebody puts that 40 in there, then the less than sign is no longer working, or the equal sign is no longer working.
Mm-hmm.
So.
Yeah. Okay, yeah, that makes sense. I thought it was more just a typo, but it's good too.
No, and in this particular case, it's not going to matter, but there are other places where the arguments are more involved, where if you do drop a constant somewhere, you don't want to have that hurt you later.
Mm-hmm. There's another thing about this kind of notation, where oftentimes when they use, so particularly in this argument, I was trying to verify it, and what they have here, like, well, it does hold. It also just completely gets rid of all the k terms in these bounds, and I know that the k is fixed, so and we're taking n large, so like we can just treat it as like a scalar multiple, really. But we have like there's some, so when you actually try to expand this out, you do end up with a couple of extra like k to the epsilon terms, and since k is one of the variables and epsilon, like I mean sorry, k to the epsilon prime, like these same epsilons that you're using for the n, and so I understand that it's fixed, but I wasn't really sure if it is something that you could just do that with.
As long as you have said earlier that epsilon is always at most 1, then you're fine.
Mm-hmm.
And so in all arguments like this, you should have, somewhere in every occurrence of epsilon, epsilon is at most 1. And then exactly as you say, if any of those terms are revised, they don't matter.
Yeah. Okay. Yeah, this is something that I wanted to check more thoroughly. I wrote out part of the argument over here, and they basically, what they really oversimplify is this. They take stuff that looks like this, and then they say, oh, we can take epsilon and epsilon prime to make this bounded above by like n to the 1 minus and epsilon double prime. And so it's ignoring.
You mean n to the negative something?
No, they use n to the 1 minus something when you have the w equals 1 case, and n to the negative something when it's w equals n case.
When I see that here we have n to the negative epsilon over 2, I don't see where you would get the n to the 1 coming from.
Well, they use, well, yeah, that's the thing. That's what's strange, because when they do this, they have this one is the one that they say is less than epsilon.
Can you blow up your screen a little bit, make it a little bit larger?
Yeah.
Okay.
Yeah. So I haven't gone through this super thorough. I like rewrote all the bounds because I wasn't fully buying the argument. And then they say, but what they say is that this thing is bounded, is of order like O of n to the minus epsilon double prime, and this one is bounded above by like O of n to the 1 minus epsilon double prime. So, I mean, which I guess is technically true, and you're taking like the epsilon and epsilon prime, which will make this just some positive number, and this will be some negative.
The thing is, we can choose, given epsilon prime. So given epsilon, we can choose epsilon prime so small that the exponent of that n is negative.
Mm-hmm.
And then my question is there a factor of n that we just missed somewhere, that it should be n times that?
Yeah, so I think, so they sometimes they average out and sometimes they don't. So I think when they originally wrote this out, they missed writing a lot of the, size of the cuspidal mu form.
What's annoying is it's not quite a miss. It's if you go back to Vanyitsluo-Sanak, in some cases they have it, in some cases they don't.
Mm-hmm.
So it's not consistent in the literature when you're looking at the sum and when you're looking at the sum divided by the number of forms.
Yeah. Yeah, as far as I could tell, when they did the original calculation, they did have it, and so redoing it with this, which gives you another like 1 over n multiplied, that's when you get these bounds. So as far as I know, this is what they're trying to match to the n to the 1 minus epsilon double prime. But if I was to try and correct anything, I can try to like be totally confident of that.
Right. I mean, the main thing is we just want to get n to a negative power, and that's going to be enough to be negligible in the limit.
Yeah. Yeah, so there's a
statement that every epsilon is at most 1.
Yeah, they say just to take epsilon prime, which can make this bounded above by n to the minus double epsilon. But I guess, you can just say or it can be changed to say like, oh, there exists epsilon prime, both less than 1, which make this true. And then
Correct.
because this is less than k, so you
Correct.
can just treat it like a fixed constant.
Exactly.
Okay.
And then one possibility, and I don't want to do this, is you could try to keep track of all the k dependents so that if somebody wanted to let not just the level grow, but the weight grow as well, you could try to handle both. To me, there's already enough features in this problem as is. Let's not worry about that.
Mm-hmm. Yeah.
Okay, Fernando, do you have anything else? Because if so, I could talk about the short note, the correction of HM.
Oh yeah, please do. No, I
Okay.
don't have anything else now.
Oh, perfect.
Do you want to screen share? Or should I?
Can you do that? I think I sent you the file. You know, the one I sent you like an hour ago.
Yes. 1 second. Sorry, I need to reopen it.
No problem. I just saw like one of your files, one of the files of mine open on your background. So I was just hoping it's that one.
There's just way too many PDFs.
Sorry.
Okay.
What we
Got
might
it.
want to do is we might want to just comment out all the random matrix theory parts of the paper. Or just, create a new paper right now that's just the number theory in the beginning.
Can you see the paper on my screen with Ella's handwriting on it?
Yes.
Yeah.
Okay, perfect. So I feel like I'm supposed to I try to track down a lot of stuff, but in this paper itself, it's very big because this lemma itself, it relies on IMT Lin lemma 3.2, which relies on lemma B2, which also depends on this lemma. So kind of basically a big bunch of IMT paper just relies on this proof being correct. So my biggest concerns were basically the fact where there were jumps in reasoning I could not follow for some reason. So in particular, could you slide down to the bottom of the page? Yeah. So especially in equation, I think, oh, sorry, up, sorry. Do you see the okay, you know what? I feel like that won't work. Sorry. Can someone share the screen? I probably should share it right now. Sorry.
Okay. So, do you want to share then?
Yeah, sorry, it won't work.
No, that's fine.
Do you not have sharing access or? No.
Yeah, I don't think. Oh no, wait, I actually do. Sorry, I thought I don't. Sorry.
If you, I can share and you can have the document open so you tell me what lines to look at in the equations.
No, it's fine. Okay. Okay, that should work. Is everybody seeing the file?
Yes.
Okay, perfect. So for the first estimate BX, right? We use the following estimate from theorem 13.7. So actually I digged through all the sources and compared them with the paper itself. So in here they're assuming that if chi is not equal to chi 0 with mod b, and then
Sorry,
in the
what paper is MV?
MV is it's actually a book. It's
it's Montgomery Vaughan. Okay, it's Montgomery Vaughan.
Yes.
Okay.
Okay,
Yep.
yeah. So they're differing. So for chi not equal to chi 0, then the E of 0 cancels out. So you get with one of those terms, right? Either 1319, 1320, or 1321. What I'm not understanding is why in 0.6 this thing is squared.
It's just a log. It's just a log term that's squared.
Yeah, but what my concern is, if you follow the theorem 13.7, there's none of those cases would actually follow the thing why it is that squared. You know, it should be either log x log b, it should be log x log bx, or log bx. None of those actually fit.
Do those theorems in Montgomery Vaughan, do they have the log p, or are they just summing chi of p?
Just chi.
Okay, I mean, I would have to check Montgomery Vaughan. If they don't have the square, that's better. It makes things a little bit smaller.
I actually can share a screen here right now. I think I have it somewhere.
Okay. The other thing is, it's not wrong to have that. It just makes the bound a little bit larger.
Okay.
And the thing is, as soon as you have a big old bound like this, you have lost all chance of having cancellation in sums. You can't have things canceling, so you can only now just basically put in absolute values everywhere.
Okay, yeah, okay. Sorry, I just like, I think I lost that file for like a very recent, but I can check that. But I'm pretty sure there was a log in there. So, but it's
Okay.
possible I'm wrong. Yeah.
I mean, it's a little bit better if it doesn't have the square, but we're
Mhm.
not going to win any of these arguments by a power of logarithm, because we're always going to have a epsilon floating in one of the exponents, and that will allow us to kill any powers of logarithms.
Okay. Okay, my so my next question, I guess, will be for here. So they're making this huge jump. So like everything from here is just follows directly from like previous reasoning, and it's all like pretty direct.
Okay, good.
And then they're doing this big, yeah, and then they're doing this big jump from like 1 over square root of n, like this line,
Mm-hmm.
to this one. So basically, like they're just basically shoving all this equation. Like this part, like when they're doing summing over chi, that makes sense. But then, like, where are they getting the r to the power of sigma n over 2 part? Like, are they just shoving it from that part? Like, I was trying to like follow it through, but without any like sufficient explanation, I could just like not put the pieces together.
Okay, so we have C. What is the function C again?
Yes, this is the b1. Sorry, I'm just gonna dig through that here. So it's, oh no, this one. It's A, which is this thing, then B, and C is just a product of B's.
Okay, so we basically want to, sorry, can you go back to that?
Oh, sorry.
Yep. Okay, so this is equation 0.5.
Okay.
Now, one thing to notice, it splits as a product of these BJs. So we just have to estimate each BXJ, right?
Mm-hmm.
And so when you have the C with all the different R's, it's just you're doing the BXJ n times.
Yeah.
Okay, so now go back to where you said there was an issue. Okay, so we have the C of R sigma. So
Mhm.
one thing is we want to just trivially estimate what is B to the R sigma.
Oh.
That's all
okay.
you're doing. That's all you're doing. So if you
Gotcha.
go back to equation 0.5,
Mm-hmm.
okay, so now in equation 0.5, just imagine that there's only one prime. And you basically, the phi hat restricts PJ to be at most R to the sigma.
Gotcha. Yeah. Okay.
Okay. There should be I'm surprised that there's no log R in the denominator. Usually there's a log R in the denominator. Can you keep it at 0.5?
I'm sorry.
It's okay. So normally you would have like a log PJ over square root of PJ log of R. I don't know where the log of R is. That must have gone someplace else. But basically, the log of PJ is at most the log of R to the sigma, so that's at most log of R.
Mm-hmm.
Or even better yet is to use like the prime number theorem. You've got log of PJ over the square root of PJ. When you sum that, that should be like PJ to the 1/2 evaluated at R to the sigma. So it should be like R to the sigma over 2.
Okay. Okay, that makes sense. Yeah.
Right.
So for the remaining ones, I think all of that, it's a bit convoluted, but it does make sense. So
Okay.
yeah, the rest does make sense.
Okay, good.
And I feel like that's for me. That's my file. Thank you for explanation of that one thing.
Yep. And again, whenever you're stuck like this, if you're stuck for too long, just send me an email, because this is the problem in that things are not often written with tremendous number of details. And sometimes I can quickly remember what was going on. Sometimes it's going to take me a while. But as soon as you see a big O, you know that the argument can't be delicate. It's only delicate when you don't have a big O and you're somehow trying to exploit cancellation and sign. So in some sense, whenever there's a big O, the argument has to be trivial and easy. When there's not a big O, when we're expanding out the main term of the Kloosterman sum, and then that hits the Bessel integral, and now we have these Ramanujan sums and everything, that's going to be the really hard argument, because everything has to be perfectly balanced. and that's where you're going to try to get some cancellation. As soon as we say, oh, let's just replace with the magnitude of the Bessel function or the magnitude of the Kloosterman sum, as soon as you do that, you've lost the ability to do any cancellation anywhere. Just think that as the rest of your stuff oscillates, your big O term is going to oscillate in sign, not in magnitude, in sign, to always align perfectly with what you need to make your quantity real and positive. You live in the worst possible world as soon as you do big O. So your only chance when you're doing big O is that it has to be trivially small. Does that help?
Yeah, I think it does. Yeah.
Okay, anything else?
Do you think it would be productive to quickly scroll through section 3 of IMT, and maybe you could give us pointers as to the stuff that you think is more likely to have mistakes, just based on what you remember? Or
No, absolutely not. Do you know why?
Because that means that we won't go through the rest as thoroughly?
No, it means you will be colored as you go through the rest and as you go through that.
Mm-hmm.
It's borderline, should I send you the stuff? And I decided I will, where my students think some mistakes are. But I want to do everything in my power to have you looking at this with an independent set of eyes.
Mm-hmm.
Because I know there are some mistakes in places. And you've already found a couple of small ones, fortunately, nothing that's going to really change the results. But it is too easy for mistakes to happen.
Okay. Okay, that makes sense.
And then if you want, we can plan on maybe every 2 days trying to have a extended support meeting and just talk about just methodically going through the paper section by section.
Yeah. Yeah, I would be okay with like just meeting every once in a while, just going through every potential typo we found, everything we might want to fix, or we don't know if it's right.
Right, I'd be happy to beat about that too.
Okay, I'm going to stop recording for now.